Our next section, 9.10, is on Syn Dihydroxylation. So this is the reaction that we can use to put two hydroxyl groups on an alkene and orient them syn with respect to each other. And there's actually a lot of different reagents that we use to do the Syn dihydroxylation reaction. One of them that I'm going to show you, this is the one that's most commonly used in textbooks, is a two-step process. We use, in step 1, osmium tetraoxide, and then in step 2, sodium bisulfate and water. And that gives us a molecule that has two OH groups where the double bond used to be, with syn orientation with respect to each other. There's actually a ton of reagents that can be used to do the Syn dihydroxylation process. The osmium tetraoxide, it works really well as a reagent, but it's very expensive and very toxic. So as a substitute for that, the most common substitute that you're going to see is potassium permanganate in hydroxide basic conditions with cold temperature. It's got to be cold. Otherwise, it's going to do more stuff than, it's not going to stop here at this particular product. So potassium permanganate and hydroxide, both of those are very cheap reagents, and they're not hazardous or toxic, so they're safe to use. But potassium permanganate is a very powerful reagent that, unless you keep it really, really cold, it's not going to stop at this particular product. It's going to continue to react with this product and make more things. We're actually going to study that next quarter, looking at what else this set of reagents can do, especially if you warm it up a little bit. So you're sort of left with this decision: do I use reagents that are really expensive and really toxic and hazardous, or do I use reagents that are cheaper but may not give me the product that I necessarily want? And it's just sort of a, whatever is more important to you. Yield versus safety, that's a decision that you have to make yourself. That you can also use osmium tetraoxide with sodium sulfate, very similar to the reagents provided in this particular example. It's just not bisulfate. And then also recently, and much less commonly, people have come up with a way to use catalytic quantities of the osmium tetraoxide. That means just very, very, very small amounts, which gets around the fact that it's really expensive and to some extent hazardous as well. So you can also use catalytic small amounts of osmium tetraoxide in a solvent abbreviated NMO, which stands for N-methylmorpholine N-oxide. And you could also do a catalytic Syn dihydroxylation with tert-butyl hydroperoxide and hydroxide. These reagents, not as common. You're going to see them as examples in your textbook, but typically the reagents that we're using to do this reaction in lab and on paper are going to be one of these three sets. So the mechanism for this reaction is not something that we're going to look at, not even sort of pseudo looking at it. We're just going to look at the process. So here's one example: potassium permanganate cold with peroxide, Syn dihydroxylation. If this wasn't a symmetrical molecule, we'd also have an enantiomer that we could draw. But because of the symmetry, those two molecules are the same thing, so we don't need to draw it twice. Here's one more example. We'll use this time an osmium tetraoxide. And again, just put those two hydroxyl groups on the same side. Both wedges or both dashes, whichever you would prefer. This reaction you can practice with conceptual checkpoint 933.